All right, 4.2 mean value theorem. Yeah, I'm going to skip that paragraph. I mean, it's an awesome paragraph, but let's skip it. Let's get right to the mean value theorem for derivatives. If y equals f of x is continuous on every point of the closed interval, so oh, that was weird. Let's try that again. Continuous on the closed interval and differentiable, I wish they didn't split up this word, differentiable at every point on its interior, and we say the open interval, then there's at least one point in C, point C in AB, at which the instantaneous rate of change equals the mean rate of change. Now, what does that mean? There's a couple ways to approach this. One is graphically, and we say that if we have a continuous function that is differentiable from A to B, we have the slope of the secant line here. If it's continuous and differentiable, there's guaranteed to be a place where the slope of the tangent line is the same. In other words, these are parallel. So if you have this slope, there's guaranteed a point where we have this tangent line and those two are parallel. It's guaranteed. If it's not continuous or it's not differentiable in the interval, it may still happen, but it's just not guaranteed. So let's look at example one. Show that the function f of x equals x squared. First of all, show that it satisfies the hypothesis of the mean value theorem on the interval 0 to 2. So in other words, does it meet both conditions? So can I write, now this is f of x equals x squared, and we know what that looks like. From 0 to 2, it looks like this. That's what x squared looks like from 0 to 2. Now, can we say f of x is continuous on the closed interval 0 to 2? But more importantly, can we say that it's not continuous there? In other words, are there any radicals in the equation? Square roots or fourth roots or sixth roots? That'd be a problem. Or any variables in the denominator? We don't have either one of these. I'm pretty confident that you could plug any number between 0 and 2 into x squared. But more importantly, there's no problems, right? So I can confidently say that. Now the problem with this is there's no work to be done, really. You just have to be able to you got to be confident that you can make that statement. All right, the next part is we need to take the derivative. 2x. Can you say f of x is differentiable on 0 to 2? Or more importantly, like I said, can we say that it's not differentiable on 0 to 2? No, we can plug anything into 2x. All right, so we've done that. We show that it satisfies. I don't know how to show it other than what we've done. It's more, make sure you're convinced that it's okay. Then find a solution C in the equation where the instantaneous velocity equals the average velocity. Or we can say the slope of the secant line is equal to the slope of the tangent line. Now we already took the derivative. We already have this piece over here. It's 2x. But usually in this equation, we write 2c rather than 2x. It doesn't matter. I don't care if you leave it 2x or 2c or whatever you want. But the convention is we write them with c's rather than x's. It's not a big deal. We want to know where that is equal to f of 2 minus f of 0 over 2 minus 0. Where does the slope of the secant line equal the slope of the tangent line? So we want 2c is equal to 4 minus 0 over 2 minus 0. So 2c equals 2, 1. Here's the secant line on my little drawing, and they say here's 2, here's 0. Right at 1, the slope of the tangent line would be exactly the same as the secant line, so slope of the secant line. There's your mean value theorem. It seems a lot more complicated than what it really is. It's really not that bad. What do we have next? Oh, here's where the hypotheses fail. Explain why each of the following functions fails to satisfy the conditions of the mean value theorem on the interval -1 to 1. Well, this is kind of nasty of them to write it like this, because this is f of x equals the absolute value of x plus 1. The square root of x squared is the absolute value of x. It's not just x. Well, if we graph this, it's the absolute value just pushed up 1. And so this function is continuous on -1 to 1, but from -1 to 1, it's not differentiable. It has a corner at 0. So not, we'll say f of x is not differentiable on -1 to 1. It has to be differentiable in the open interval. It has a corner right in the middle. So now we're just not guaranteed that there is. As a matter of fact, there's not. The slope of the secant line from -1 to 1 is 0, but down here we don't have the slope of 0. If this happened to be a parabola, then we'd be okay. If it did this, then this would be 0, and we'd have a tangent line that has a slope of 0. If it was x squared, we'd be fine. On letter B, this is a continuous function. That's polynomial, and it's differentiable everywhere. This is a continuous function, and it's differentiable everywhere. The only problem could exist is where they meet each other, at 1. So if I plug 1 into this, we get 4. If I plug 1 into the bottom one, we get 3. So f of x is not continuous at x equals 1. Or on, I should say, well, at x equals 1, but not continuous on -1 to 1, more to the point, on that interval. Specifically, it's not continuous at 1. Oh. It needs to be brackets. 1, 2, not 1, 3. Thank you. 1, 2. So one fails the differential part, one fails the continuous part. And it just missed it, right? It's right at the end point where it's bad. But it has to be good there. Applying the mean value theorem. Let f of x be this, right here. Point A is -1 f of -1, which is 0. If you plug -1 in, 1 minus 1 is 0. And then 1, 0 over here. If you plug 1 in, you get 0 also. Find a tangent line to f in the interval -1 to 1 that is parallel to the secant AB. So I need a point, and we need a slope. That's the question. Find a tangent to f. Find the tangent line. I need f prime of x. That's 1/2 1 minus x squared to the -1/2 times -2x. So the 2's cancel out, and we get x over the square root of 1 minus x squared. Now that's the derivative. That's the, let's say, the instantaneous velocity, or the slope of the tangent line right there. So x, actually we use c over square root of 1 minus c squared needs to be equal to y2 minus y1 over x2 minus x1. So I need c over square root of 1 minus c squared. I need that equal to 0. Well, how do you make a fraction 0? Make the top 0, right? So c happens to be 0. So c is equal to 0. So we have the point 0 comma something. Well, if I plug 0 in there, I get 1. 0, 1, and I know the slope has to be 0. Slope has to be 0. So y minus 1 is equal to 0 times x minus 0, which is really the equation y equals 1. I needed the instantaneous, or the slope of the tangent line, to equal the slope of the secant line. All right, but we got the answer. Here's the answer. But I mean, what did we do? This is y is equal to the square root of 1 minus x squared. If I square both sides, add x squared over, what's x squared plus y squared equals 1? What is that? Circle, isn't it? It's a circle. But when you solve for y and you only write the positive part of the square root, that means the top of the circle. Now here's our 2 points, right here and right here, -1, 0, and 1, 0. Here's your secant line. Now the question is, where on this circle is the slope of the tangent line 0? Well, right at the top, right here, right where x is equal to 0. And that's exactly what we said, except we said it was c equals 0 instead of x. But it means the same thing. That's what happened. That's what we did. Now, we could have just looked at the graph and answered that exact same thing. I think if everyone could have said, if I would have said, well, here's the secant line, where is the tangent line, where does it have a slope of 0? I think everyone could have seen that it was up here. But we have to know the process. We have to be able to do the process right there. The physical interpretation of this. When I was 15 years old, I know it was 15 because I had my learner's permit, and my dad worked for the railroad, and he was stationed out in Wyoming. He was a traveling mechanic. He had this huge truck with a crane on it, and he fixed the equipment that fixed the tracks. He fixed that equipment when they broke down. So it was kind of this domino effect. So he couldn't bring his truck past Bradshaw, Nebraska. Every time he would travel, and then he'd come home over the weekends. So we'd have to go out and get him so he could spend time on the weekend, and then when the weekend was done, he'd have to go back out. So my dad traveled a lot. So my mom and I are driving out to get him. I'm driving, having a great time because I'm 15. I'm just driving, and I get to drive a long time. That doesn't happen very often. Like, how many times have you driven for an hour and a half? Probably not very often, right? So I'm excited about it. Well, I get a little tired, so my mom and I switch out at a gas station, I remember. And so we're driving into the middle of Nebraska. And in the middle of Nebraska, there's nobody. You see one car every hour on the highway where we were. But on the highway, they had these little squares spaced out, right? And so we drove past these 2 squares, and there was a cop sitting up on top of the hill, and he pulled us over. But the cop clearly wasn't doing he didn't have a radar gun. He wasn't following us. He didn't really radar us. What happened was there was a plane up in the air. The plane saw us cross the square, and then they timed how long it took us to get between the 2 squares. And then they got our average velocity, and it was 55 on the highway back then, or that highway. And let's say we must not have been going too fast because we only got a warning. Let's say the average velocity between those 2 was 60. If the average velocity was 60, does it make sense that it's guaranteed that at least one moment in time we were going 60 miles per hour? In other words, how could you average 60 if you never got over 58 miles an hour? That's impossible, right? So they pulled us over, gave us a warning, and we were on our way. But that's what happened. So they're saying that, well, if the average is 60 miles per hour, then the instantaneous velocity is guaranteed to be 60. And that's exactly what this is. Average, the average rate of change is equal to the instantaneous rate of change somewhere. Now that only can be true because speed is continuous, right? I can't go 50 miles per hour and then automatically jump to 30 miles per hour. It can't be discontinuous. It has to be continuous, right? If I go from 50 to 30, I have to go every mile per hour in between there, at least for a brief moment in time. All right, so that's a really long way to say that right there. I don't want to jump right to increasing and decreasing. I want to go practice this a little bit. So we're going to jump around the notes a little bit. Find number 2 and 4. Find 2 and 4. It's there somewhere. A, state whether or not the function satisfies the hypothesis of the mean value theorem on the given interval. So A here on f of x equals x to the 2/3. Can I say that f of x is continuous on 0 to 1? Well, we got to be careful here because this is the third root of x squared. But can't we take the third root of anything? We're okay with that. So check, yep, that's good. I'm okay with that statement. That seems to be good. F prime of x is 2/3 x to the negative 1/3. That's 2 over 3 x to the 1/3. Uh-oh. What would be bad for this derivative? What value? 0 would be bad, wouldn't it? But f of x has to be differentiable on the open interval. So remember, 0 would be bad. Are we good or are we not good? Are we good to say that? We are good. It's not differentiable at 0, but we don't have to include 0. So we're good there. We just made it. An endpoint was bad, but that's okay for differentiable. So we're good to go. B, if it satisfies, and it does, find each value of c in the interval AB that satisfies the equation. That equation right there. Now we already took the derivative. It's sitting right there. So 2 over 3c to the 1/3 is equal to, I need f of 1 minus f of 0 over 1 minus 0. So instantaneous rate of change equals average rate of change. That value is guaranteed to exist because we met the hypotheses. If I plug 1 in, 1 to the 2/3 is 1, 0 to 2/3 is 0, over 1 minus 0. 2 over 3c to the 1/3 is equal to 1. Multiply it over. Divide by 3. 2/3. Raise both sides to the 3rd power. So c is 8 over 27. There. That's the answer that we're looking for. So when x is 8 over 27, the secant line, the slope of the secant line is the same as the slope of the tangent line. That's what we found. Everybody good? On number 4, can we say that f of x is continuous on 0 to 4? Can we say that? I think we can. I don't think there's anything we can't plug into that one. So that's a check. We're good there. I'm not going to do the derivative on this one. I'm going to appeal to our knowledge of graphs. Taking the derivative would take a while. There's the absolute value of x. What happens when we put minus 1 on the inside? Which way does it go? To the right one, correct? Yeah, to the right one. So we have a corner at 1. So f of x is not differentiable on 0 to 4. It fails at 1. So if you look at the instructions, it says, if it does, find the value. So number 4, we're done. We're done with that one. There's mean value theorem. Any questions on the kind of the process on what to do on those? Because we kind of changed gears a little bit now. We have 2 topics for today. We got mean value theorem, and we got increasing and decreasing. I love the first definition. It's brilliant. Let f be a function defined on the interval I, and let x sub 1 and x sub 2 be at any 2 points on I. F increases on I if x sub 1 is less than x sub 2, which leads to f of x sub 1 is less than f of x sub 2. That is just absolutely genius. And here's what it's saying. If you have 2 points, if you have your first point and your second point, if the second point is higher than the first point, it's increasing. No, seriously. Seriously. I know you don't believe me, but seriously, that's what it means to increase. It's genius. They formalize it, right? They just got to say it. And this is going to blow your mind, but guess what? If point 1 is up here and point 2 is down here, if point 2 is lower than point 1, guess what the function's doing? Yeah, it's decreasing. Yeah, seriously. No, really, seriously. Okay, so this is, I call it duh. Okay? Yeah, no kidding. This one's not so much duh. This one's what we're trying to get at right here. It says if f prime is greater than 0 at each point of a to b, then f increases on a to b. So if we have a function that increases, then the slope of the tangent line will be positive. Even if it increases concave up or concave down, the slope will be positive if we have an increasing function. If we have a decreasing function, the slope of the tangent lines will always be negative, as long as it's decreasing. So if you have a decreasing to increasing function, negative slopes, negative, hits 0, and then goes positive. If you have negative to positive slopes, we have a minimum, right? We have a minimum there. And then if you have a maximum, well, that means your slopes go from positive to negative, all being positive increasing to all being negative decreasing. So that's a local maximum. That's more important. This one is, yeah, no kidding. This one's calculus. We need this one. All right, that's how we're going to use it. Example 5 says determining where graphs rise or fall. The function y equals x squared, and then they kind of explain it. Well, I know what y equals x squared is. It decreases to 0 and then increases after 0. But let's do the calculus on it. Y prime is equal to 2x. Now we're looking to see where these change signs, where the derivative is positive and where's the derivative negative. So where's our point of interest? Like where do functions change signs? When x is, or when y is 0, right? When y is 0, you can go from positive to negative. So we want to set the derivative equal to 0. This little statement, setting the derivative equal to 0, is sometimes, not always, worth a point out of 9 on a free response question. Just setting it equal to 0. Even if you have no clue what to do on a test, take the derivative and set it equal to 0. You might get a point out of that. You might not. All right, anyway, x equals 0 is where our derivative changes signs. Possibly, not necessarily. So now we throw that on a number line and test each side. Test -1 and 1. So now we want to know if the slope of the tangents are negative or positive. We want to know if the function's increasing or decreasing. So we plug -1 not into the original. I don't care about the points. I care about whether it's increasing or decreasing. So we plug this into the derivative. 2 times -1 is -2. So this function decreases from negative infinity to 0. We already knew that. It decreases to 0. Now we're going to plug 1 into the derivative, and 2 times 1 is positive, so now this function apparently increases after 0. Yeah, we know that. It increases now. So decreases from negative infinity to 0, and increases from 0 to infinity. We got to know the process, because what if I give you something that you don't know what it looks like? We have to know the process. Number 6, determining where graphs rise or fall. What does x to the third minus 4x probably look like? Kind of that S kind of. It probably looks like this. So what does this function do? It increases till it gets here, and then what does it do? Then it decreases, and then it increases. All right, let's do the process to get that answer, to get that evaluation of what happens here. So what we're going to do is we're going to take the derivative, 3x squared minus 4. We're going to find out where the slopes are 0, where they change sign. So in other words, up here and down here. So 0 is equal to 3x squared minus 4. Taking the derivative and setting it equal to 0 on a test could be worth 1 or 2 points. It could be, not every time. So 3x squared is equal to 4. X squared is 4/3. X is plus or minus 2 over square root of 3. We're going to put those on a number line. -2 over square root of 3 and +2 over square root of 3. All right, there they are. But now I got to find some values. I'm not going to, if I don't let you use a calculator, I'm not going to give you these crazy numbers. But I've done this a couple times today. So 2 over square root of 3 is a little more than 1. So it seems like -2 would be good, 0 would be good, and 2 would be good. If I don't let you use a calculator, this will factor, and we'll get some nice rational numbers. All right, -2 into the derivative, right there, or right here, either one, it's the same thing. 12 minus 4 is positive. I don't even care that I know, what is it, 8? I just care that it's positive. So this says this function increases from negative infinity to -2 over square root of 3. Yeah, we kind of knew that was going to happen. Increases, because we know what an x to the third kind of looks like. 0 is -4. Negative. Oh, yeah, now it decreases in between, decreasing. And then plug 2 in, 12 minus 4 is 8. It increases again. So increasing from -infinity to -2 over square root of 3. And then 2 over square root of 3 to infinity. And then decreases from in between. But guess what we're going to do tomorrow? Tomorrow we're going to say, well, if our function increases and then decreases, what's happening right here? What's going on here? A local maximum. So this is a local max. Today we're just focusing on increasing and decreasing. What if our function decreases and then increases? What's going on right here? It's a local minimum, isn't it? Local minimum. Local minimum is happening there. That's a sneak peek into tomorrow. Other consequences. The derivative of constants is 0. So if you have f of x is equal to 7, well, 1, 2, 3, 4, 5, 6, 7. What if we had that line right there, y equals 7? What's the slope of that line? 0, right? So f prime of x is 0. That's what that's saying, the corollary 2. Functions with the same derivative differ by a constant. So if, in other words, f of x equals sine of x plus 2, and g of x is sine of x minus 6,000, what's the derivative of both of those? Cosine of x, right? The constant doesn't change what the derivative is. So if functions have the same derivative, then they differ by a constant. They differ by that much. Find the function whose derivative is sine of x and whose graph passes through the point 0, 2. Whose derivative is sine of x. So if I wrote the derivative of f is sine of x, then what is what we call the antiderivative? What's f of x? Be careful. Negative cosine, right? Negative cosine. But f of x is negative cosine of x plus a constant. Remember that if you have functions with the same derivative, they differ by a constant. Well, this over here, now we can find the constant. Without this, if they don't give us that, there's our answer. That's as much as we can do. If they give us what's called an initial value, then we can find the c. And we do initial value problems a lot more on the second half of this semester. Because we're going forward. We're going forward with derivative, then we'll go backwards with antiderivative. So this section just kind of introduces it. All right, so what do we do with this? Well, the y is 2, and the x is 0. Now, you got to be careful because not everything, when you plug 0 into functions, they don't always become 0. As a matter of fact, the cosine of 0 is 1. So c is equal to 3. So our final answer, because they gave us initial condition, f of x is negative cosine of x when we know that it's plus 3. If it's not 3, it won't go through that point. Has to be 3. All good? All right, let's do some practice. I think we already, oh no, do I have more? Oh yeah, I have one problem left and then we get to the practice. A function f of x is an antiderivative of a function f. If you're going backwards, forwards derivative, backwards antiderivative. And we call it antidifferentiation. Finding velocity and position. And I had to look this up. I figured this, but I want to make a note to myself. It is assumed that the position at 0 is 0. So we're starting at 0 at time 0 for these problems. Find the velocity and position functions of a body falling freely from a height of 0 meters under each of the following sets of conditions. A, the acceleration is 9.8 meters per second squared and the body falls from rest. So that means A of t is simply 9.8. It's a constant. Now the instructions say find the velocity and position functions. So the velocity function is 9.8t plus c. We're going backwards. We're doing antiderivative. It says that the body falls from rest. So that means v of 0 equals 0. At time 0, we're falling from rest. So 0 equals 9.8 times 0 plus c. So c ends up being 0. So our answer for velocity is 9.8 t plus 0. We don't write that. It also says find the position. All right, let me ask you this. Think about it. If the velocity's function is 9.8 t, what is position plus c? Anybody got it?
You divide the coefficient by 2.
Okay, yep. Yep, what's 9.8 divided by 2? 4.9 t squared, right? 4.9 t squared. Because if we took the derivative of that, we'd multiply times 2, we'd get 9.8, and then we would reduce the power by 1. And it's assumed that s of 0 equals 0. We're starting at 0. So c is equal to 0 for position. So there's the position function. B is slightly different. Slightly different. And I'm not being sarcastic. It's just slightly different. The acceleration is 9.8 meters per second squared, and the body's propelled downward with an initial velocity of 1. So instead of just dropping it, we're just giving it a little throw. We're starting it with a velocity. So the acceleration, again, is a constant. That hasn't changed. Velocity is 9.8 t plus c. So that doesn't change. But now, velocity of 0 is equal to 1, not 0. So 1 is equal to 9.8 times 0 plus c. So c ends up being 1. V of t is 9.8 t plus 1. Now get the position function. What's s of t? It's almost the same. Very close. Wouldn't it be 4.9 t squared, but plus what? Plus t, yeah. Derivative of t is 1, and then plus c. But again, they say we assume that we're starting at the same position, at position 0. So on this one, c is 0. That means 4.9 t squared plus t is our position function. This is mainly second half of the semester. And in AB, it's the second semester. They get behind us a little bit, or a lot. Questions? Anyone want to move to AB? You can't. You're stuck. Find the local extrema. So I'm doing tomorrow a little bit early, but I want to do it. We're not doing the whole thing here. I want to do a little early because this is the DCA. So you'll have a DCA over this topic, and we're going to include tomorrow's stuff on the DCA as well. So this is kind of the beginning of it. Find the local extrema. F prime of x, and we've already done it. This is another x to the third. We already can predict what's going to happen. That's going to happen right there again. But x to the thirds are nice to work with. We're going to take the derivative, and we're going to set it equal to 0. That's your mantra for this chapter and whenever you do derivatives. Take the derivative, set it equal 0. Take the derivative, set it equal to 0. We do that a lot. That's why I had you factor stuff out. Remember me saying that? I go, hey, we got to factor stuff out because we're gonna see what makes derivatives 0 later. Well, here we are. X minus 3 x plus 1. So x equals negative 1, x equals 3. So this local maximum is at negative 1. This local minimum is at 3. I already know that. But here's the process. We plug this on a number line, negative 1, 3. These are called critical points. Negative 2, 0, and 4. Those would be nice values to check. Now we plug this into the derivative because we want to know if the graph is increasing or decreasing. So negative times a negative is a positive. So the graph is increasing there. Plug 0 in, negative times a positive is negative. And we plug 4 in, positive times a positive is positive. So now we're asked what are the extrema. So we have a local max. Let's not worry about the y values at x equals negative 1. And then the graph goes from decreasing to increasing. And so we have a local minimum at x equals 3. And we'll build on that tomorrow. And then we'll get our full DCA and what it looks like. Everybody good there? How about we try, what time we get out of here today? 6 at 26. All right, we got a decent time here. Let's try to get these two done and then we'll probably call it good. Try 16. Try the process. Listen, you already know what a parabola looks like. You would not need calculus for this problem at all. But we really need to practice the process. Then I got something kind of cool to show you. So g prime of x is 2x minus 1. Set that equal to 0. X equals 1/2. So that's where the vertex is, right, of this parabola. That's where the vertex is. And we know it's going to go minus positive. It's going to go decreasing, increasing. But here's the process. We throw that on a number line. We go 0, plug 0 into the derivative. That's negative 1, negative. Plug 1 into the derivative. That's 2 minus 1. That's a positive. And there we have it. And we knew that was going to happen. So increasing from negative infinity to 1/2 and decreasing from 1/2 to infinity. There's the answer to that question, to the homework there. But I got something kind of cool for you. If we take a parabola, ax squared plus bx plus c, do you remember how to find the x coordinate of the vertex? There's a tiny little formula for it. You guys remember? Negative b over 2a. Remember that? Did negative b over 2a and then took that and plugged it back in. That was your vertex. That was your point. Well, isn't the vertex where the tangent line, where the slope of the tangent line is 0? Right? You agree with that too? So if we took the derivative of this, what would the derivative be? 2ax plus b, right? Okay, and then we set that equal to 0. And then we minus b and divide by 2a. So there's your vertex formula. So you've been using kind of calculus for a while now. You've known the negative b over 2a for a long time. But that's where it comes from. I can finally show you where that comes from. Up until now, it wouldn't have made any sense. No applause necessary. That's okay. No, not if I have to ask. Sorry. Okay, 18. Let's try 18. Let me ask you a question first. What's happening at 0 for this function? A what now? Go ahead. Oh. Right. So what's happening graphically? Yeah, on the graph. Can't do it. That's exactly right. He's like, can't do it. Can't put 0 in here, right? So what is there on the graph? Vertical asymptote, right? Vertical asymptote. Well, if I have a vertical asymptote, let's say at 0, and what if the function looked like this? It went from something like this to increasing to, well, this, I'll just show you what it looks like, to decreasing. That means the tangent lines are all positive over here and then all negative over here. So they changed. So we can change signs over zeros, and we can change signs over asymptotes also. So when you take the derivative, this is x to the negative 2, k prime of x is negative 2x to the negative 3. Negative 2 over x to the third. Now I told you that we set derivatives equal to 0. We also want to know where derivatives are undefined. And this is undefined at x equals 0 because we have a vertical asymptote there, and our derivatives can change signs over that vertical asymptote, and actually it does. So we go 0, negative 1 and 1 we could choose. If I plug negative 1 into the derivative, negative over a negative is a positive, so increasing. If I plug 1 into the derivative, negative over positive is a negative, decreasing. So increasing from negative infinity to 0, decreasing from 0 to infinity. And this is actually what the graph looks like. Increasing, when you jump over the asymptote, this decreases from left to right. So we want to know where the derivatives are 0. We want to know the derivatives are undefined. Those two places. All right, that's it. We're kind of out of time. I put a few problems too many on here, but that's kind of what I want.